Hello class, this is how we're going to learn about the properties of area and how to find the area of complex figures. So first we have to talk about sets. So we're going to learn about the properties of area in terms of sets. So a set is essentially just a group of objects that we call elements. So for example, down here in this numerical example, we have a set U, and it's the integers from 1 to 9. So each element is an integer, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And a subset is what it sounds like it is. It's a set that's contained inside another one. And we use this notation. It looks like a less than or equal to sign, but it's rounded. And so, for example, this set A is a subset of set U because every number in A is a number in U. Each of them is an integer from 1 through 9. Now, the union of two sets is what we get when we take all the objects that are in either the first set or the second set or in both. So for example, what would the union of sets A and B look like? And the symbol for union is this U, this big U shape. Well, if you look at it with a Venn diagram, we end up with this picture, and all the numbers that are in A or B are inside the shaded area, and so it would be the integers from 2 through 8. Now, intersection is when we look at just the elements that are in set A and in set B, so they have to be in both. And we use this upside down U shape. So what would the intersection of sets A and B? Well, the only number in both of them is 2. So the intersection of sets A and B is 2. And we use these curly brackets to represent a set usually. And note that the order of the elements in the set isn't important because it's just a group. So, and they all have to be distinct. You can't repeat an element inside a set. So in this example, we have two congruent triangles, and we want to calculate the area of each one. So why don't you try that? Well, they both have the same base and height, so they both have the same area, just 52.92. And which transformations will always give us another triangle with the exact same area? So which of these four will do the job? Well, hopefully you said the basic rigid motions: transformation, rotation, and reflection. So explain the answer here. Why did you pick these answers and not dilation? There are a lot of correct answers. One of them is to say that, so if you have two congruent figures, you can use these transformations to map one onto the other. And so they would have the same area because they're congruent. And it couldn't be a dilation because dilation could change the size of the figure. In this example, you want to calculate the area of the shaded region. So I'll zoom in a little bit. So try to figure out the area of the entire shaded region, and I'll show you my solution. So the way I broke it up was I said, okay, there's two triangles. So that's where this 2 in front comes from. And the area of a triangle is 1/2 base times height. And they both have the same base and height, so their combined area is 9. We also have this rectangle in the middle, and its area is 21. And so we add all these numbers together, and we get 30. So I'd just like you to take a moment to write down the process that we did in order to figure out the area of this figure. So one possible answer is this one. We're basically just writing down what we verbalized before. Okay, here we have two overlapping triangles, and they overlap to form the smaller triangle DGC. And they tell us these dimensions. So AD is 4, DC is 3, and CF is 2. I'd like you to take a moment to try to calculate the area of figure ABGEF. So that's this big shaded figure. Well, hopefully you started off by figuring out the area of these two larger triangles, ABC and DEF. So the area of ABC is 14, and the area of the smaller one is 5. Now, can we just add those together and say the area is 19? No, we can't, because we'd be counting the area of the smaller triangle 2 times. So we got to find the area of that smaller one and subtract that from 19, because we can't double count it. So the answer is 17.65. And same idea, explain how we determine the area of this figure. So try that and I'll show you my answer. So there's one possible answer. You're just saying that you have to subtract that overlap because you don't want to count twice. And here's another one. You have a triangle that's been cut out of a rectangle. You can find the area of just the shaded region. So kind of like just the donut part, not the whole. So what's the area of that? Well, the rectangle has that area, and the triangle has this area. And so we just want to subtract them because we were taking the triangle out of the rectangle. So 224.64. And explain how you found the area of that region. Put that into words, and I'll show you my solution. So exactly what we said before. You just subtract the area of the triangle from the area of the rectangle. So this leads us to our properties of area. So the first few are fairly straightforward. The other ones we'll talk about a little bit more. So number one, the area is just a number that quantifies the size of the figure. And in this case, we're talking about a set. So you can think of a figure as a set, like a set of regions. And remember, the area doesn't have anything to do with the shape of the figure. So you can have two different shapes with the same area. Regions have the same area. That seems pretty straightforward. Looked at that with the congruent triangles. And we've learned these formulas before. So rectangle length times width, triangle 1/2 base times height. Now maybe this seems new, but we applied this before. Oops, let's go back. So a polygonal region is the union of all of the triangles that make it up and don't overlap. And if you add up the area of all those triangles, you would get the area of the polygon. So it's a process called triangulation, and we'll look at an example of what exactly that means. Our fifth property is that the area of the union is the sum of the two areas, but you take away where they overlap. So we saw that before. And finally, if you have a region with a hole in it, you just subtract the two areas. So let's look at that fourth one for a moment. We already saw before that the area of this shaded figure was 30, right? We have these two triangles and a rectangle. But we could actually turn this into only triangles, and we should get the same answer. So let's see what happens. Would our answer change if we instead drew that diagonal there? What's the area now? So why don't you try to calculate the area of the four triangles that come together and see if you get 30. And if you did that process, you should indeed get 30. So it doesn't matter how you break it up. As long as these triangles don't overlap, you add them together, their areas together, and you get the same area. Okay, here's an example of overlapping figures. So if you want to figure out the area, one way to do it was you could add together the area of these triangles and subtract the overlap. All right, you could also do a triangulation here. Maybe that's easier. All depends on the type of figure you have. So going back to sets, if we're talking about the area of that entire figure, it's like the area of a, looking at the union of the two areas, or the two figures, I'm sorry. So the idea is we can't just add their areas together, we gotta subtract that overlap in the middle. And that overlap is the intersection. Just that section in the middle. So one way to think about the area of the union of two shapes, it's the area of each one minus the area of the intersection. That's exactly what we did to solve this problem before. We saw that the area was this number, and we got that by adding the 14 and 5 and subtracting 1.35, which is the overlap. So we really used this formula. We just did it with numbers before. Okay, and here's one where you have set A, which is a subset of a set B. So set A would be the whole in this case. And so to figure out the area, we just subtracted the two. So this is a way that you can show it using our set notation. So you can subtract sets as saying, if you take set B and take away set A, that's what you're left with. In this lesson, we learned different properties of area and then use them to find the area of complex figures. Thank you for watching this video.